In this video, we will see thin pressure vessels. So this is the basic definition of thin pressure vessels, and to differentiate between the thin and thick pressure vessels, we use denote by T. Denote is outside diameter, and T is the thickness of this vessel. So if denote by T is greater than 20, then we call it as thin pressure vessels, and if it is less than or equal to 20, then it is known as thick pressure vessels. So that is how we differentiate between thin and thick. And in thin pressure vessels, there are radial stresses which are negligible, so we can neglect the radial stresses, and in thick pressure vessels we have to consider radial stresses. So this is a technical difference between thin and thick pressure vessels, and mathematically we can differentiate it with this relation. So now if we see stresses, then first is longitudinal stresses which are along the line, which is the central line of the vessel. So you see, if we cut this vessel into half, then there is particular stress developed in this region which we can see to balance the equilibrium. So on the inner side of this vessel there will be pressure, so which will be pushing it towards the left, and this stress is sigma L, which is longitudinal stresses, which will be pulling it towards the right, so it will be in equilibrium. So sigma L, if we want to calculate, which is along the length of this vessel, then it will be simply P denoted by 40. P is a pressure inside the vessel, T is a thickness, and denote is outside diameter of this vessel. So this is a simple relations, and a lot of the times direct numerical is asked from this equation. If we see other type of stress in this vessel is circumferential stress, which is perpendicular to the length of the vessel, which if we cut the vessel into half like this, then on the thickness of this vessel along the length there will be stress developed, which is a hoop stress. So on this particular edges, two edges, there will be hoop stress, and if we balance it with the pressure, and then we get the relation sigma c, which is a hoop stress or a circumferential stress, which is P denoted by 2t. So it is also called as hoop stress sigma h. So P denoted by 2t, P denoted by 4t. Sigma L and sigma c are two relation for pressure vessels, which are generally thin pressure vessels. Now if we derive more relations, then if we see element on this particular vessel, then there are sigma L on longitudinal direction and sigma hoop on perpendicular direction. So we directly know that there is no shear stress is acting. So sigma 1 will be hoop stress, sigma 2 will be sigma L, because hoop stress is more. Here there is a 2 division factor, here is 4 division factor. So sigma C is 2 times sigma L. So that is also a direct 1 mark numerical asked in gate examination, the relation between sigma L and sigma C. So now this is our element. If we calculate in plane maximum shear stress, so in plane maximum shear stress based on these two stresses will be sigma 1 minus sigma 2 divided by 2. So that will be equal to P denoted by 80, because if we subtract this and divide by 2, then P denoted by 80. So in plane means we have to use this formula, but if you want to calculate absolute shear maximum, tau maximum, then maximum of these three formulas, sigma 1 minus sigma 2, sigma 1 divided by 2, and sigma 2 divided by 2, whichever is maximum. So we know here that sigma 1 divided by 2 is maximum, because P denoted by 40 here, and if we take sigma 2 divided by 2, then we get P denoted by 80, and also sigma 1 minus sigma 2 divided by 2 is also P denoted by 80. So here sigma 1 divided by 2 is maximum, so that will be absolute tau maximum. So that is a basic difference between in plane and absolute. If they ask in plane, then we have to use this formula sigma 1 minus sigma 2, and for absolute we have to use maximum of this, and we are putting modulus because to have the absolute values of maximum. So here if it is negative, then also it is maximum, because magnitude they are asking tau maximum in terms of magnitude, not in terms of positive or negative. So if we calculate now strain, then first is hoop strain. So hoop strain is a maximum principal strain. So here's epsilon 1. So for generalized Hooke's law, we have two stresses in two opposite directions. So 1 by E sigma 1 minus mu sigma 2. Here mu is a Poisson ratio. So we have two stresses, so we have to use generalized Hooke's law. That will be equal to, it is in diametral direction, circumference direction. So delta D divided by D, and if we keep values of sigma 1 and sigma 2, we get this relation. Similarly, if we calculate for longitudinal stress sigma epsilon L, then epsilon 2 will be 1 upon E sigma 2 minus mu sigma 1 delta L divided by L, because it's in longitudinal direction, and we get this formula after placing sigma 2 and sigma 1 in this formula. So sigma 1 is sigma 1 is this PD naught by 2T, sigma 2 is PD naught by 4T here, if we see. Now the last part is that volumetric strain. So for volumetric strain, delta V divided by V, that will be equal to, here circumferential direction is there, so 2 times circumferential plus epsilon L longitudinal, because epsilon x plus epsilon y plus epsilon z is epsilon V. So here epsilon x and epsilon y are hoop stress and epsilon z is longitudinal stress. So 2 times epsilon 1 plus epsilon 2, we get this relation after placing epsilon 1 and epsilon 2 in this form. So here we get this formula. Now sometimes they ask pressure vessels, thin pressure vessels which are spherical in shape. So here for pressure vessel, all the direction are same, so all direction are hoop stresses sigma 1, and that will be equal to P denoted by 4T. Here hoop stress is P denoted by 2T, here hoop stress is P denoted by 4T. So if we place all this formula and calculate for spherical pressure vessel, then tau maximum in plane will be sigma 1 minus sigma 2 by 2, which will be 0 because both are same. Tau maximum absolute will be sigma 1 by 2, which is P denoted by 8T. For strain, it is epsilon d divided by d, which is P denote by 4T 1 minus mu, because sigma 1 and sigma 2 both are sigma 1, both are same. And for volumetric strain, it is simply 3 times epsilon strain, so we have to multiply this formula by 3. So this is how we calculate for volumetric and normal strain, and this is it for the thin pressure vessel, and see you in the next video. Thank you guys.